This is the second section of chapter 5, the travelling salesman problem, and this section is about using a minimum spanning tree method to find an upper bound. Now you'll remember from the previous section we said there's no efficient method for solving the travelling salesman problem, so it's all about finding out whether our solution is any good, how good our solution is, and we do that by finding an upper bound and a lower bound for the minimum weight. So we can use a minimum spanning tree to help us find an upper bound for the maximum weight that sort of will go to every vertex and return to our starting position. Now, if you are given a network in a question, then the best way to find a minimum spanning tree, well, there's actually two ways, is we can use either Kruskal's algorithm or Prim's algorithm to find a minimum spanning tree. If you are given a distance table or a least distance table, then the best way to find, I'll put least there because it could be a least distance table. The best way is to use Prim's algorithm, because we know how to use Prim's algorithm on a distance table, and we can apply that to a least distance table. Now, once we found the minimum spanning tree, if we find the weight of the minimum spanning tree and times it by 2, this gives us an upper bound for the travelling salesman problem. Now, why would the minimum spanning tree times by 2 give us an upper bound? Well, imagine this is a minimum spanning tree and we can work out the weight of this. So this is a minimum spanning tree for a network. We're basically saying, right, if I traversed every arc twice, so let's just put some different coloured lines in here to show that I'm going along each of those arcs twice. That's like the maximum I have to do to visit every vertex. So walk to that vertex, walk back, walk to another vertex, walk back. Now, there's probably a more efficient way of meeting every vertex, maybe sort of just traversing this one twice, but what it does, it gives us an upper bound for the travelling salesman problem. Now we can improve on this upper bound, we can get a better or lower upper bound by looking for shortcuts. So a shortcut may mean using edges which are in the original network, which are not in the minimum spanning tree. Or it may mean actually repeating repeating a fewer number of arcs than repeating every single arc. So that will give us a better or a lower upper bound. Right, so on this question it says use Kruskal's algorithm to find a minimum spanning tree for the network on the right. Okay, so Kruskal's algorithm says the first thing we need to do is to list the edges in order of weight in ascending order. So AC and AD are both weight 3, so that goes first. So maybe I'll just cross these off as I do them. I'll uncross them afterwards. Then I've got CE, which is 4, so we'll add that on, CE. Then we've got 3 that are 5, so let's put them in alphabetical order, BF, CD, and DE. Then we've got a weight of 7, that's DF. Then we've got 2 of weight 8, BD, and FG, and then 2 of weight 9, AB, and EG. Right, so with Kruskal's algorithm, we start with the edge of least weight, one at the start. So that is AC. So we put that into the tree. Then AD we add, CE we add, we don't add it if it forms a cycle. BF is the next one, we add that. So remember, Kruskal sort of jumps around, doesn't it? Can jump around and they all get connected. C to D, we're going to reject that because that forms a cycle. Then DE, that also forms a cycle, D to E, so we'll reject that as well. Then DF, yes, we can add that. Then B to D forms a cycle, gets rejected. FG, we can add that. And I've now gone to every vertex. So this is my minimum spanning tree here. Okay, so here's a drawing of that minimum spanning tree, and the weight of this minimum spanning tree is going to be 4 plus 3 plus 3 plus 7 plus 8 plus 5, and that gives 30. Okay, so if we have a look at part B, hence find an initial upper bound for the travelling salesman problem. Well, it's going to be the weight of the minimum spanning tree times by 2, so it's going to be 30 times by 2, which is going to be 60. So we're basically saying that one of the maximums we can do is basically to go down each one of these edges or arcs twice, which would give us a length of 60. Now, there's obviously, well, not obviously, but there's probably a simpler way of doing it, or a quicker way of doing it, so that I start and finish at every vertex or at the same vertex. So for example, one solution, let's say we were starting and finishing at E, is we could start at E, C, A, D, B, F, G, and then back to E. So that is going to be less than 60. So in fact, that would be 4, 7. This way would make 10, 18, 23, 31, 40. So it's less than our upper bound. There may even be a shorter way of doing it, but that's just one example of going to every vertex and coming back to the same place that we started. The table of least distances for a network is given below. Find an initial upper bound for the travelling salesman problem for this network. That means finding the weight of the minimum spanning tree. And since we've been given a distance table, so we've been given a distance table or a table of the least distances, the easiest way to find a minimum spanning tree is to use Prim's algorithm. So that's what we're going to do. Now, normally with Prim's algorithm, the question will say starting at vertex A, B, whatever it is. Here we're not given a starting vertex, so we're going to choose, I'm going to say starting at vertex A. Right, so since we're starting at vertex A, that means we cross out row A, we number column A1, and we look for the lowest weight in column A, and that's going to be 11. Okay, so we're starting at A, we're now going to B, and that's going to be a weight of 11. Okay, so that means we can now go to column B, label it 2, and we cross out row B, and then we look for the lowest weight in either one of these two columns here, 1 or 2, and that's going to be 8. Okay, so the next vertex to be added is going to be D. That's going to be a weight of 8. So that means now we're going to cross out row D and look at column D. which we'll label 3. So now we're looking for the lowest weight in either column A, B, or D, and that's the lowest weight is the 13 here in C, row C. So the next vertex to be added is C. Now the C is 13 away from A, so actually we've got this, C is here, and that's 13. Now don't take any notice of the arrows, it's not directed network, so it's basically just showing the weight between those two vertices. So now we label C as 4, we've crossed out row C. Now we look at these 4 columns and find the lowest weight in any one of these 4 columns. That's going to be the 14 here. Okay, and then once you've crossed out all rows, your algorithm is now finished. So E was connected to D, and that's a weight of 14. So let's draw what maybe this network might look like. Sorry, our minimum spanning tree. So there we go. So that's what our minimum spanning tree would look like. So if we want to find an upper bound for this traveling salesman problem, it's going to be the weight of the minimum spanning tree times by 2. So that's going to be 11 plus 13 plus 8 plus 14 times 2. So that will be 46 times by 2. So we have 92 as an initial upper bound for the traveling salesman problem for this network. Right, starting with the initial upper bound found in example 4. Now that initial upper bound was 92, 46 times by 2. Use a shortcut to reduce the upper bound to below 70. Right, so this is the minimum spanning tree we found using Prim's algorithm in the last example, and we basically got 92 by saying 13 doubled, 11 doubled, 8 doubled, 14 doubled, and going along each one of these edges twice. Now if we keep the same starting vertex, now what we could do is just go A, B, D, E, and then E to C. So using the least distance table, I can see that the least distance between C and E is 18. So what I could do is put this in here. So, and the weight of that is 18. So I could say that to visit every vertex and come back to A, I could go A, B, D, E, and then take the shortcut of 18 to C, and then the 13 back to A. So let's write down what that route is. So A, B, D, E, C, A, and let's work out what the weight of that is. So that would be 11 plus 8 plus 14 plus the 18. So this 18 here, that's the shortcut. You get that from the table. Plus 13. Now what weight does that give us? Okay, so that gives us a weight of 64. Well, that's below 70, which is fine. Now I've just chosen one way of doing it. There may be different ways of getting an upper bound to below 70, maybe choosing a different starting vertex or choosing a different shortcut. But typically what we want to do is to find an edge which isn't in the minimum spanning tree, which is in the original network, which we can get either from a diagram of it or from the table of least distances here. Okay, so the table shows the distances in miles between 8 cities. A politician has to visit each city starting and finishing at A. She wishes to minimize the total distance traveled. Find a minimum spanning tree. Okay, so since this is a table of distances, we're going to be using Prim's algorithm. And since we are starting at A, we label column A1 and we cross out row A. Now we look for the smallest weight in column A, which is 47. So we know that we start at A, we're going to B, and that's going to be 47 miles. We want to see where to go from B, so we label column B2 and we cross out row B. So now looking at both rows A and B, where do I find the smallest weight? So the smallest weight is C there, which is 84. So the next town we go to is town C, and that's going to take 84 miles to get there. Now, you need to be careful here because we're going to town C from town A. So that's 84. So now we're going to label column C3, and now we're going to look for the lowest weight in one of these first three columns here. Now that looks like it's 120, so we'll circle 120. So now we're going from A to E, so I'll put this here, so 120 there, and E. So I label column E4, and I've crossed out row E. So now I want to find the lowest weight in columns A, B, C or E. And that looks like 131 down here. So 131, which is in row H. So that's going to get labelled as 5. Now that's going from E to H. So E to H, and that's a weight of 131. Now the lowest weight in any of these columns here is the 70, that sort of sticks out. The 70 in row F. So F we're going to label as 6. Now that F goes from H, so we go to F there, and that is 70. So now we try and find the lowest weight in one of these 6 columns here. Looks like actually 144 there. So 144, that's in row G. That's going to be 7. Now that connects F to G, that's 144. So we're going to have G here, 144. Now I want to try and find the lowest weight in any of these columns that we've got left. Actually, it's looking for the lowest weight in this row here, which is going to be the 155D. Now our algorithm's finished, and we just need to join G to D, and that's 155. Okay, so here's a drawing of what the minimum spanning tree might look like. Now I'm going to write down the weight of this minimum spanning tree. So 155 plus 144 plus 70 plus 131 plus 120 plus 47 plus 84 gives a weight of 751 miles. Okay, part B, it says hence find an upper bound. Well, that's just going to be the weight of the minimum spanning tree times by 2. So 751 times by 2 is 1,502 miles. Okay, part C, it says use shortcuts to reduce this upper bound to a value below 1,300 miles. Okay, so looking at the diagram, this is where the diagram helps. I really want quick ways of looping back without having to retrace my route. So can I close off this loop here between B and C is 121. So it'll be quicker to do that 121 there than going forwards along A and then back again. forwards to C and then back again, because that would be 47 times by 2, 84 times by 2. That adds more than 121. So we can stick a shortcut there of 121. And also, when we get all the way to D here, we don't really want to come all the way back. It would be much better to say, right, let's go from D all the way back to A and close that loop off. And then if we look in our table, D to A is 382, which is quicker than all of those. That'll be less than adding all of those together. That's more than 382. So I'll just put 382. So we really need to write down what our tour is. So the tour is what's going to start at A, take us all the way around to all of the vertices and then back to A. So tour of network starting and finishing at A. Starting, I'll just put finishing at A. So one possible route would be A, E, H, F, G, back, and then D back to A, and then A, C, B. So we'll just write that down. So A, E, H, F, G, D, back to A, C, B, finishing at A. And we want to see what the weight of this is. So the weight of this route is the weight of the minimum spanning tree plus our shortcuts weight of minimum spanning tree plus shortcuts, because with our shortcuts we don't actually need to traverse any of the edges twice. So if you have a look, we start there, we only do these ones once, we go around that edge, and then AC, and then BA. So the minimum spanning tree, which is all the edges in blue, plus our shortcuts, so that will be 751, plus our shortcuts of 382 plus 121. Let's see what that gives us. Well, that's 1,254 miles, and that is below the 1,300 miles that they wanted in the question. So you should now be able to do exercise 5B on pages 112 to 113, and this section was about finding an upper bound by finding the minimum spanning tree, either by using Kruskal's or Prim's algorithm, multiplying this by 2, and then trying to improve our upper bound by looking for shortcuts.